Hey everyone, Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival. And in this video, I'm going to address a quick question. Can elements exist as molecules? So let's begin as we often do by setting forward a couple of definitions. First, an element. An element is any material that cannot be decomposed into simpler substances. A more practical way of saying this is elements are composed of just one type of atom. Now we also know that there is such a thing as a molecule. And a molecule is a group of atoms bonded together. So we need at least two atoms to make a molecule. And if you think carefully about these two definitions, they are not mutually exclusive of one another. It is indeed possible for a molecule to consist of just one type of atom. So let's take a look at a few of these. So let's limit our discussion about elements and molecules today to just non-metal elements. Now, among non-metal elements, there certainly are those that exist as single atoms when we find them in nature. Elements like helium and neon. So when we want to write these particular elements out, we simply write their formula as their elemental symbol, He for helium or Ne for neon. But this is actually rather rare. Consider another example, nitrogen. We don't find nitrogen as isolated atoms in nature. Instead, when we find elemental nitrogen, we almost always find it bonded to a second nitrogen atom. This creates a molecule of nitrogen with the formula N2, in which the subscripted 2 is letting us know that there are two atoms of nitrogen per molecule. Take the example of oxygen as well. The oxygen you're breathing right now is not isolated oxygen atoms, but rather oxygen atoms bonded to other oxygen atoms to form a molecule with the formula O2. Again, the subscripted 2 lets us know there are two oxygen atoms per molecule. These subscripts are so important because it's possible for elements to form molecules with differing numbers of atoms in them. Let's look at oxygen again, but now let's look at a different version of oxygen, one called ozone, in which there are 3 oxygen atoms per molecule. When we have a situation like this, where an element can make molecules of varying sizes with varying numbers of atoms, we call these two different forms of the element allotropes. The word allotrope comes from Greek terms meaning other form. So let's move on and look at some more allotropes of varying elements that make molecules. Here's an allotrope of phosphorus that contains 4 phosphorus atoms in a beautiful tetrahedral arrangement. We would write out a formula for this of P4 because there are 4 atoms per molecule. Another interesting allotrope is one of sulfur, which contains 8 atoms. So this molecule would be a molecule of S8. This trend can continue, and in fact some elements exist in molecules so large that their formulas are kind of hard to write. Consider the very abundant element carbon. One allotrope of carbon contains many atoms of carbon, all bonded together in a network that's virtually endless. So we might try to write a formula for this allotrope of carbon as C infinity. But rather than do that, we simply give it a special name. We call this allotrope of carbon graphite. So whether we're dealing with monatomic elements, diatomic molecules of elements, polyatomic molecules, or even polymers of elements, it is indeed possible for elements to exist as molecules. Thanks for watching, everyone. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. And I'll see you on my next video.